What does the temperature of invisible moisture in the air have to do with, legally binding multi-million-dollar construction contracts?
Quite a lot, actually.
Yeah, I mean, you sent us this massive, highly technical legal file titled FIDIC Painting Scope of Work.docs. And it turns out the answer is basically absolutely everything.
It really is.
When you first asked us to look into a painting contract for today's deep dive, I have to admit, my mind immediately went to, like, a weekend DIY project.
Oh, sure, like painting a living room.
Right. You go to the hardware store, you stand in front of that massive wall of color swatches, buy a few cans of eggshell white, lay down some old newspaper, and just, start rolling.
Yeah.
It's straightforward,
Yeah.
right? A purely visual upgrade.
Right, and if you miss a spot with your roller, you just go back over it the next day. The stakes are incredibly low.
Exactly.
At worst, you have a slightly uneven finish in your guest bedroom. But the document you sent us, it operates in a completely different universe.
Love to.
The FIDIC Red Book, for those who might not spend their days immersed in international engineering contracts, is essentially the gold standard framework for global mega projects.
Right.
So when a document like this talks about painting, it is not talking about aesthetics, it's talking about survival.
Survival.
Yeah, it's about protecting billions of dollars of critical infrastructure from literally dissolving into the atmosphere.
And the mission for our deep dive today is to decode this incredibly dense contract language for you, the listener.
Right.
We want to uncover the hidden, almost obsessive complexity behind how these massive industrial sites are protected.
Places like oil refineries, power plants, chemical facilities.
Yeah, exactly. We are going to see exactly how these projects control chaos, enforce quality, and manage cost down to the absolute microscopic level.
It's intense.
It is. It's this high-stakes world where industrial engineering, intense chemistry, and strict legal boundaries all collide.
It really is a fascinating collision of disciplines. You have meteorology, metallurgy, chemistry, thermodynamics, and contract law.
All in a painting contract.
Right, all masquerading under the deceptively simple banner of a painting job.
Okay, let's unpack this. Because to understand how you even begin to paint a massive industrial site, you first have to understand how the project organizes millions of individual components.
Yeah, I really do.
You can't just walk out onto a 100-acre facility and tell a crew, hey, go paint that maze of pipes over there.
No, absolutely not. That would be a disaster.
You need a blueprint for the chaos. And in the source material you sent, that blueprint is called the WBS, or the work breakdown structure. I like to think of it as the project's DNA.
The DNA is a perfect analogy. The work breakdown structure is the foundational coding framework that the employer uses to categorize and identify every single piece of work.
Before they even buy the paint.
Exactly. Before a single drop of paint is even purchased, it's designed to completely eliminate ambiguity.
And looking at this document, that DNA is overwhelmingly specific. I mean, the overarching discipline code for this scope is SP, for surface preparation.
Yeah.
But then it drills down into these incredibly granular Level 4 and Level 5 activity codes. I was looking at this and thinking, why do they need a completely different legally binding code just because a pipe is stainless steel versus carbon steel?
Wow.
Like, why does stainless steel get an S1 code and carbon steel gets an SPO code? Isn't paint just paint?
What's fascinating here is why this rigorous coding is absolutely essential. It's not just administrative busywork so someone in a back office can track a spreadsheet.
Okay.
It is a critical engineering safeguard. Carbon steel and stainless steel have entirely different metallurgical and chemical properties.
Right, they're fundamentally different metals.
Exactly, and because of that, they require entirely different surface preparations. For instance, the document notes that stainless steel requires specific treatments like pickling, passivation, and solvent degreasing.
Wait, hold on. Pickling, like cucumbers.
I know it sounds funny.
What does that actually mean in a metallurgical sense?
Well, in this context, pickling means submerging the steel in a highly corrosive acid bath. Yeah, it's used to strip away superficial impurities, rust, and scale left over from the manufacturing process.
Okay, that makes sense. And what was the other one? Passivation.
Right. Passivation is a subsequent chemical treatment that helps build a microscopic protective oxide layer on the surface of the metal.
Okay.
Carbon steel doesn't undergo that exact same chemical regimen. So if a contractor gets confused and treats stainless steel the exact same way they treat carbon steel.
Like, say, using the same abrasive blasting grit.
Exactly. You don't just get a bad paint job. You trigger something called galvanic corrosion.
Galvanic corrosion.
Yes. It happens when two dissimilar metals come into contact in the presence of an electrolyte, like moisture in the air.
Oh, boy.
They essentially act like a battery, generating an electrical current that rapidly destroys one of the metals.
That sounds bad.
It is.
Mm.
The structural integrity of the pipe is compromised from the inside out. So the WBS coating ensures there is absolute, undisputed clarity on what material gets what exact chemical treatment.
Preventing catastrophic mix-ups.
Exactly.
Wow. Okay, so the WBS acts like a barcode system that dictates the precise chemical survival plan for every single valve, beam, and pipe.
Yes, that's exactly it.
But that raises a massive logistical question for me.
Which is?
Once everything is barcoded and you know it needs to be painted, how does the contractor actually get paid for doing it? We're moving from the categorization of the WBS to the surprisingly complex rules of physical measurement. And honestly, the geometry of how they bill for this work kind of blew my mind a little bit.
The measurement rules in a FIDIC contract are really where the abstract engineering meets the hard economics.
Yeah.
Every single euro exchanged between the employer and the contractor is tied to a very specific, undisputed physical measurement rule outlined in this scope.
Right. Let's look at how they measure pipe work. The document says pipes, which can range anywhere from a tiny quarter-inch instrument line to a massive 44-inch main, are measured in linear meters.
Right.
But here's the kicker. They are measured along the central line, meaning the measurement goes right through all the inline fittings, through the complex elbows, the branching T's, the reducers.
Right, straight through.
You don't measure the outside curve of an elbow joint. You just draw an imaginary line right down the middle of the pipe. I mean, is that just lazy? Doesn't that make the measurement incredibly inaccurate?
It might seem counterintuitive at first, but it's actually a brilliant piece of contract design.
Really?
Think about it. Tracing the true external surface area of a complex curved elbow or a branching T-joint out in the field is an administrative nightmare.
Oh, I guess you'd be out there with a tape measure all day.
Worse, it would require complex calculus for every single fitting, and you'd have inspectors and contractors arguing over fractions of a millimeter.
That sounds exhausting.
It is. By standardizing the measurement to the center line, both the employer and the contractor agree on a simple, verifiable geometric truth. A straight line is easy to measure. The contractor slightly loses out on the outside curve of an elbow, but they gain on the inside curve. It averages out the complexity and saves thousands of hours of arguing.
That is incredibly pragmatic. But then there are items of inline equipment, like valves, relief valves, butterfly valves, and those are explicitly excluded from that linear measure.
Right, they are handled differently.
They're enumerated.
Yeah.
You literally just count them one by one. One valve, one unit rate.
Keep it simple.
Exactly. But the rule that really made me laugh was regarding structural steel and large vessels, which are measured in square meters.
The voids rule.
Yes. There is a strict rule that says no deductions shall be made for voids not exceeding 1.0 square meter.
Right.
So if I have a massive steel wall with a 1 square meter window cut out of it, the contractor still gets paid as if they painted the window. They are literally getting paid for painting thin air.
It does sound like paying for thin air, I'll give you that. But you have to consider the labor mechanics of the job.
Okay, how so?
Think about the time, the precision, and the taping required to carefully paint the inner edges of that small void.
Oh, right.
Having to cut in around it without making a mess. That meticulous edge work often takes significantly more time and manual effort than simply taking a large spray gun and blasting paint over a flat, solid surface.
So it's compensation for the extra work.
Exactly. The rule inherently balances the increased cost of labor against the saved volume of paint material.
Okay, that makes sense. You're paying for the hassle, not the paint.
Exactly.
But here is where I have to push back. Because there is one measurement rule in the document you sent us that completely stopped me in my tracks.
Let me guess.
General pipe supports.
Yeah.
The brackets holding all these heavy pipes up, the contract states they are measured by weight,
Yes.
in kilograms.
I know it sounds odd.
They're categorized in bands,
Yeah.
like under 5 kilos, 15 to 25 kilos, up to over 100 kilos. Wait, why are we weighing pipe supports on a scale to figure out how much paint to use instead of just measuring their surface area like the structural steel? Paint covers surface area, doesn't cover weight?
It is a great observation, and again, it points to the sheer pragmatism required to manage a mega project.
Okay.
Pipe supports are geometrically chaotic. They aren't just flat plates.
Right.
They are made of attachment plates, weird angled brackets, spring hangers, U-bolts, and threaded rods. Trying to mathematically calculate the exact Square meterage of a 15-kilogram clamp with a dozen nuts and bolts is practically impossible.
Right, you would need an army of surveyors out there just measuring individual screws.
Precisely. So the engineering industry analyzed decades of data and realized there is a highly reliable correlation between the weight of a standard fabricated steel support and its total surface area.
Oh, wow, so they just mapped the weight to the area.
Exactly. By throwing that support on a scale, or simply looking at its fabricated shipping weight, you instantly know what weight band it falls into.
That's incredibly smart.
It turns an impossible geometric puzzle into a fast, undisputed number. It makes estimating the volume of paint and the economics of the labor completely manageable.
Okay, so we have the WBS barcodes to prevent chemical disasters, and we have these wildly pragmatic measurement rules. Imaginary central lines, paying for thin air, and weighing brackets on a scale.
Yep.
So we know exactly how many linear meters of pipe and kilograms of supports we are dealing with. The next question is, what exactly does that measurement by the employer?
Right, the scope of the rate.
Because the source document reveals that painting is really only the tip of a massive hidden iceberg of costs.
Yes. Section 7 of the document specifically outlines the rate inclusions and exclusions.
Okay.
When the contractor submits their composite unit rate, say 50 euros for 1 linear meter of pipe, that single number has to legally cover a staggering amount of invisible preparatory work.
Here's where it gets really interesting, because the inclusions read like you're booking an all-inclusive resort, but for hardcore industrial construction.
Pretty much.
That single rate for a meter of pipe obviously includes the supply of the paint and the wages for the painter, but it also includes all the surface preparation.
Right.
The solvent washing, the heavy abrasive blasting, getting rid of all the toxic waste. It includes meticulously masking off all adjacent areas.
Everything.
And it includes all the costs for working at heights, meaning the contractor has to design, build, maintain, and eventually dismantle the scaffolding.
Yeah.
All for that same base rate.
And they cannot charge a single cent extra for any of those preparatory steps. It is entirely baked into the baseline cost.
But the most shocking inclusion to me was this line right here.
Yeah.
It says all temporary weather protection screens and enclosures as required to maintain the specified ambient conditions.
Yeah.
They essentially have to build a customized microclimate around the pipe.
If we connect this to the bigger picture, this entire section is about the transfer of risk and the avoidance of legal disputes.
Okay, how so?
Weather is the ultimate enemy of a strict construction schedule. If it rains or if the wind picks up dust, you physically cannot apply these chemical coatings.
Right, the paint won't stick.
Exactly. By explicitly stating that temporary weather protection is included in the base rate, the employer is legally insulating themselves from nature.
Oh, I see.
They are telling the contractor, I am paying you for a finished, fully cured, painted pipe. If it rains for 3 weeks straight, I am not paying you extra to build a heated tent over it. That is your risk to manage.
It completely shifts the burden.
It does.
And just to be clear, the document is also very strict about what is excluded from that rate, which also protects the contractor.
Great, goes both ways.
The painting contractor is not responsible for the thermal insulation of the pipework. They are not responsible for fabricating the steel itself. And they aren't responsible for securing overarching statutory permits from the government. But everything strictly inside the boundary of surface preparation and coating, that is entirely on them.
But if the contractor is absorbing all of that weather risk and eating the cost of the scaffolding and the enclosures, what is stopping them from just rushing the job?
That's a good point.
What stops them from slapping the paint on quickly to save on expensive labor hours?
And that leads perfectly into Section 9 of the contract, which is quality assurance and inspection. Because the employer isn't just trusting the contractor to do a good job.
No, definitely not.
We are transitioning from macro-level logistics and billing to a microscopic battleground.
Yeah.
The standards enforced here, before a single drop of paint touches the steel, are intensely strict.
It starts with the personnel themselves. The inspectors overseeing this work cannot just be someone with a clipboard and a good eye for detail.
Right.
The contract mandates they must hold a specific industry qualification, like a NACE or AMPP Coating Inspector Level 2 certification.
NCE and AMPP.
Yeah, they are rigorous international authorities on corrosion engineering. These inspectors are highly trained specialists who doubly understand the underlying chemistry of how steel degrades.
And they're using highly specialized tools to enforce these rules. The document dictates that the paint thickness, the DFT or dry film thickness, must be measured in microns.
Microns, yeah.
We are talking about fractions of a single millimeter. And then there is a process mentioned called holiday testing, which, despite the name, has absolutely nothing to do with taking a vacation.
Far from it, unfortunately.
The source specifies it as pinhole testing. How does that actually work? Are they just staring at the pipe with a magnifying glass?
No, human eyes are completely insufficient for this level of quality control. Holiday testing involves using a specialized piece of equipment, often an electric wand or a sponge connected to a power source.
An electric wand.
Yeah. The inspector sweeps this electrified wand over the fully dried, coated surface. Paint is an insulator, but if there is even a microscopic gap, a pinhole, or a thin spot in the coating, which is known in the industry as a holiday, the electrical current will jump through that tiny gap to the conductive steel underneath.
Wow.
It arcs, completes the circuit, and triggers a loud alarm.
That is wild. They are literally electrifying the paint to find invisible holes. Why is that necessary?
Because a single microscopic pinhole is all it takes for corrosive chemicals or ambient salt air to reach the bare steel.
Right.
Once those elements reach the substrate, corrosion begins to spread laterally underneath the paint film. It's called subfilm corrosion.
Oh, so it rusts from the inside.
Exactly. The coating might look perfectly fine and intact on the outside, but the structure underneath is hollowing out and decaying from within. The electric wand finds the flaw before the rust can even start.
Unbelievable. But the rule that fascinated me the most crucial environmental rule in the entire document, is about temperature.
Ah, the dew point.
Yes. The contract states that the substrate temperature, meaning the physical temperature of the steel itself, must be at least 3 degrees Celsius above the dew point before any coats can be applied.
Yes.
Why is meteorology suddenly a legally binding part of a painting contract?
It is arguably the most critical scientific rule in the entire document. The dew point is the atmospheric temperature at which moisture in the air condenses into liquid water.
Okay.
If the temperature of that cold steel pipe drops too close to the dew point, invisible microscopic condensation forms on the surface of the metal.
Wait, even if it isn't actively raining?
Exactly. It can be a completely clear sunny day, but if the humidity is high and the steel is cold enough, moisture is forming on a microscopic level.
Oh, wow.
If a contractor sprays a highly engineered, incredibly expensive chemical coating over that invisible layer of moisture, the paint will not adhere to the steel. It mechanically adheres to the water.
And water eventually evaporates.
Yes, thermodynamics takes over. The moisture eventually tries to escape as vapor, pushing up against the coating and causing the paint to blister, flake, and peel off in large sheets.
Ouch.
You have essentially guaranteed the catastrophic failure of the coating system. This contract takes the complex physics of meteorology and thermodynamics and turns them into a strict, binary legal compliance issue.
Wow.
If the steel isn't a full 3 degrees above the dew point to provide a safety margin against humidity fluctuations, you stop working. Period.
And what happens if the contractor thinks they know better and paints anyway, and the inspector catches them?
That's a bad day for the contractor.
The contract specifies that all non-conforming work gets hit with an NCR, a non-conformance report.
Yeah.
And the contractor has to blast all that expensive paint off, fix the issue, retest it, and reinspect it entirely at their own cost.
Yeah.
The employer doesn't pay a single euro for the mistake. It is a ruthless system of accountability.
It's ruthless, but entirely necessary when you are dealing with critical infrastructure.
But enforcing these microscopic standards, hitting exact microns of thickness, hunting for pinholes with electric wands, maintaining that 3-degree dew point margin, it requires some incredibly heavy, aggressive industrial processes.
It's very intense work.
We are talking about high-pressure, abrasive blasting to clean the steel, utilizing volatile chemical solvents, and often doing all this inside dark, confined spaces.
Yeah.
This naturally brings us to the human element, keeping the actual workers safe while they execute this grueling work.
Section 10 covers health, safety, security, and environment, or HSSE.
Right?
And just like the WBS coding and the geometric measurement rules, safety is not treated as a separate optional guideline or a polite suggestion from an HR department. It is rigidly defined as a contractual obligation.
The contractor must submit specific documents before they even step foot on site. The document mentions RAMs, risk assessments and method statements, and COSH assessments.
Yes.
What do those actually do on the ground? How do they protect a worker?
RAMs are essentially a step-by-step survival guide tailored to a specific task. A method statement breaks down exactly how a dangerous task, like setting up scaffolding inside a chemical storage tank, will be executed safely.
Right.
The risk assessment maps out every possible way a worker could be injured during that task and legally mandates the exact preventative measures required.
And the COHH assessment.
COHH stands for the Control of Substances Hazardous to Health. In painting, you are dealing with highly volatile organic compounds, toxic thinners, and hazardous heavy metals.
Dog carry stuff.
Very. A COHH assessment tracks exactly how those chemicals must be stored, ventilated, and handled to prevent workers from inhaling toxic fumes or absorbing chemicals through their skin.
And it's not just the chemicals themselves, it's the physical environment. The hazards listed in this document are intense.
Oh, yeah.
You have the blinding dust from abrasive blasting. You have confined space entry where oxygen levels can drop instantly. You have hot work like welding happening near newly applied, highly flammable coatings.
And you also have the management of the waste itself.
Right.
When you sandblast a massive steel vessel to strip away old rust, you are left with tons of contaminated blast media. Sand or grit mixed with toxic heavy metals.
You can't just leave that lying around.
Exactly. You have empty paint tins lined with hazardous residues. You have drums of used solvent waste. The contract mandates strict waste management plans for the removal and disposal of all of this.
When you sit back and really imagine the physical reality of this job, it is staggering. I'm picturing a worker wearing full respiratory gear, thick chemical-resistant gloves, and a protective suit, dragging a heavy, high-pressure abrasive blasting hose inside a dark, confined metal vessel.
It's grueling.
They are fighting the physical environment, they are fighting the clock, and they are fighting the strict rules of the contract, all while trying to achieve a surface cleanliness that will literally be inspected with an electric wand down to the micron.
This raises an important question about how modern engineering contracts view safety and environmental stewardship.
How so?
Well, historically, in construction, safety might have been viewed as a secondary concern, something separate from the actual task of building or painting. But in this FIDIC document, the waste management plan and the hazard assessments are fundamentally baked into the scope of work.
Right, the safety protocol is just as legally binding as the WBS barcode or the linear meter measurement.
Precisely. If a contractor can apply the paint perfectly, hitting the exact micron thickness, passing the electric pinhole tests, and managing the dew point, but they cannot safely and legally dispose of their contaminated blast media according to their approved plan, they are in breach of the FIDIC contract.
Oh.
They haven't completed the scope of work. In this high-stakes environment, safety and environmental compliance are legally indistinguishable from the physical act of painting.
So what does this all mean for you, the listener? We started this deep dive with a stack of legal paper you sent us, the FIDIC scope of work, and an image of a simple, low-stakes weekend DIY painting project.
Right.
But what we uncovered is a highly orchestrated, multidisciplinary symphony designed to control chaos.
A massive undertaking.
Exactly. We looked at the DNA of the project with the WBS coating, ensuring zero chemical mix-ups and preventing galvanic corrosion. We navigated the bizarre but brilliant geometry of billing, where pipes are measured through imaginary central lines, contractors get paid for painting thin air, and chaotic steel brackets are simply thrown on a scale.
We saw how a single euro unit rate acts as a massive legal shield for the employer, transferring the risk and cost of scaffolding and weather manipulation entirely to the contractor.
And we explored the microscopic battleground, where highly trained inspectors hunt for invisible pinholes with high-voltage wands and track the thermodynamics of the dew point, all while workers execute physically grueling tasks under strict, legally binding safety and environmental mandates.
It's incredible.
This hidden layer of extreme rigor, this obsession with microns and temperatures, is exactly what keeps the industrial world functioning safely around you every single day. Without the rules in this contract, the infrastructure we rely on simply wouldn't survive.
It really completely reframes how you look at the built environment.
It really does.
I would offer this final thought for you to mull over. The next time you drive past a massive industrial plant, an oil refinery, or even just a large steel suspension bridge, don't just look at the static structure itself. Think about the invisible microscopic battles that were fought over dew points, the fractions of a millimeter of paint thickness, and the electrified pinhole tests. Think about that intense, legally binding chemistry that is quietly, at this very moment, keeping that giant structure from crumbling into rust.
It really makes you appreciate the fact that when all this intense engineering and contract law goes exactly right, you don't notice anything at all. Thank you for sending us this fascinating document, and thank you for joining us on this deep dive. We will catch you next time.
If you're interested in the templates, please visit our shop, the link is in the description.
Thanks for watching, please subscribe and see next time.